As part of Tool 1, it is expected that you would be able to determine the formula of a hydrated salt by drying it to a constant mass. Before we begin, there are some key concepts that will be helpful for you to understand. What is a hydrated salt and what is water of crystallization? A hydrated salt is essentially any compound that is able to include water molecules within its crystal structure. Take, for example, an ionic compound. We know that they exist in a crystal lattice. Often within that lattice, there's space for water molecules. When those water molecules are trapped inside of that crystal, they are called the water of crystallization. Water of crystallization is present in lots of different compounds, for example, gypsum, washing soda, and copper sulfate. For the rest of this explanation, I'm going to focus just on copper sulfate. But of course, note that IB can ask you questions on any hydrated compound. If you haven't already watched the video on Tool 1, determining the empirical formula, I'd recommend you watch that before you continue. From that video, you should recognize the setup. The setup for drying to a constant mass pretty much is the same. In the empirical formula 1, we heated up a metal and we allowed it to react with oxygen, and then we determined the empirical formula of the metal oxide that was formed. It's a pretty similar setup here, except this time we're going to remove the lid from the crucible. So you'll have a crucible or maybe an evaporating basin, and you'll put your compound in it, the hydrated version of the compound, and you'll heat it. What should happen when you heat this hydrated compound is that the water should evaporate. And when the water evaporates, what remains is the anhydrous or dehydrated version of that compound. So for example, copper sulfate as the hydrated version is a very distinguishable blue colour. So you'll start with a blue powder. When all of the water has been removed, you'll be left with just a white powder. As with the empirical formula experiment, this one is really all about the masses and the change in mass. So for that reason, you'll make 3 main measurements. First, you'll get the mass of just the crucible by itself. Note that they can also use an evaporating basin or an evaporating dish as well. It doesn't really matter. You just need a piece of equipment that's able to withstand strong heating and can hold the compound. So your first one is just the empty crucible by itself. Then you'll add whatever the compound is and get the new mass. The compound that you add will have the water attached to it. Then you'll heat the compound. After you've heated it, and all of the water should be lost, you'll get your new mass. The difference between these two should be the water. All that should change when you heat it is that the water should be lost. The difference between the third measurement and the first measurement will be the compound itself. So for example, this might be just the CuSO4. What we want to do is use the ratio of the masses of CuSO4 to H2O. When we have the ratio of those masses, we can use that to determine what X represents. Let's process the data that we have collected, quantitative and qualitative. We notice that the qualitative data for this is that it starts as a blue powder. It's a common misconception that students have that the hydrated version of this must surely be a solution, but not necessarily. It can still be a solid crystal and have water molecules trapped between its ions. So the copper sulfate starts as a blue powder, and when I heat it fully, it should turn to a white powder when all those water molecules have been lost. The differences between these masses are what will represent the mass of water and the mass of the copper sulfate. I know that heating this compound is what causes the water to be lost. So the difference between these two is the mass of water that's present. That works out at being 0.43 grams. I know that what should remain at the end is just the copper sulfate. So the difference between the first mass and the last mass should be my mass of only copper sulfate, which works out at being 0.77 grams. Now that I know the masses of each one, I can link that to their molar masses to determine the number of moles of each one. The molar mass is easy. I just calculate it based on the values on the periodic table. Then I can determine the number of moles using mass divided by molar mass. Once I have the number of moles of each, I want to turn them into a whole number ratio. So in order to do this, I divide both of them by the smallest number, which is the number of moles of copper sulfate. That gives me a ratio of 1:4.98 for the copper sulfate to water, which I can round to 1:5. Remember that it's an important Tool 3 skill to be able to use approximation and estimation appropriately. Therefore, I can determine that the formula is CuSO4.5H2O. An important skill as part of Inquiry 3 is to be able to explain assumptions that you are making when you formulate your conclusions. This experiment is based on the idea that when I heat the compound, the water of crystallization is lost. I assume that the compound itself isn't decomposing, breaking down, or oxidizing in any way. I'm also assuming that all of the mass that's lost is because the water is being lost and not because of anything else, such as the compound itself being lost. I'm also assuming that I do actually manage to get rid of all of the water of crystallization from that compound. These are 3 important assumptions, and you can use these to explain why you do not get the perfect ratio. Now let's discuss a level easy paper 2 question. This question is worth 3 marks, so if you want to pause the video and set a timer for 4.5 minutes, and then I'm going to talk through the worked solutions. The question tells you that solid copper 2 chloride absorbs moisture from the atmosphere to form a hydrate of formula CuCl2xH2O. The student heats the sample because they want to determine the value of X. They obtain the following results. What they want you to do is find out what is the ratio of copper chloride to waters, i.e. what is the value of X. So we know that first of all, they've changed it from being a hydrated version to the anhydrous version. That means that the difference between those 2 values must be the water that is lost. So 18.360 minus 17.917, that tells you the mass of water that was present in that compound. And I can easily turn that mass of water into a moles of water using N is equal to M divided by the molar mass. Then I can do the same thing for the copper chloride. I know that I start with an empty crucible and my final mass measurement is for the copper 2 chloride without any waters present. So that final mass value is the mass of the crucible and the copper chloride. That means that the difference between these 2 values must be the mass of the copper chloride. Again, I can easily turn that into a number of moles of copper chloride using N is equal to M over MR, with the molar mass of copper chloride being 134.45 as I get from the periodic table. Now that I know the ratio of copper chloride is to water in terms of moles, I can divide them by the smallest number to make it a whole number, and I get 1 is to 1.95, which I can approximate as 1 is to 2, and so I determine that the formula of this is CuCl2.2H2O, meaning that for every 1 copper chloride, I have 2 water molecules. Now let's discuss a medium level paper 2 question. This question is worth 6 marks, so if you want to pause the video and set a timer for 9 minutes, and I'll discuss a worked solution. The question tells you that in a class experiment, the students were asked to determine the value of X in the formula of the hydrated salt for barium chloride with XH2O. The instructions, they measured the mass of the empty crucible and the lid. They added approximately 2 grams of the hydrated barium chloride to the crucible and recorded the mass, so I know that this is the first mass value. Then they heated the crucible using a Bunsen burner for 5 minutes, holding the lid at an angle so the gas can escape. We know that this is important because the H2O has to be able to leave the hydrated salt. So after they allowed it to cool, they reweighed it, including the lid and all the contents, and then they repeated steps 3 and 4. Why they would repeat steps 3 and 4 is they want to make sure that all of the gas, all of the H2O has escaped. This experiment is called drying to a constant mass because you should only get a constant mass once all the water has been lost. So let's analyze their data and see has this happened. I know the mass of the crucible and the lid, so this is your empty crucible. That's the first value. The second value includes the barium chloride and the water with it. The third value includes it after it has been heated. In an ideal situation now, all of the water should have been lost. To confirm that all of the water has been lost, you heat it further. Because when you heat it further, and if you come back and get pretty much the same value, it tells you that heating makes no more difference. From that, you can deduce it would only not make a difference if all the water had already been lost. So what I'm checking to see are my second 2 values the same. So I can see for trial 1, those 2 values are the same, and trial 3, they're pretty much the same. There's actually quite a difference in trial 2. Because there's a difference between the first and the second heating, that tells me that after the first heating, all of the water must not have been lost, and they realized that when they heated it a second time and the mass was still decreasing. So the further work that these students would need to carry out before they can process the results would be to heat it again. Ideally, if they heated it again and they received a value of 21.865 from a third heating, then they would know, okay, that must mean that all the water has now been lost. The next question asks you or tells you that in the third trial that the students noticed that after the heating, the crucible had turned black on the outside. And they want you to suggest what may have caused this and how it might affect the calculated value for X. So one of the things I know is that when I see black on the outside of a crucible or the outside of any piece of equipment after it's been heated, it's because soot has been formed. And soot is formed because of incomplete combustion. So a reminder that incomplete combustion occurs when oxygen is a limiting reactant, and instead of forming CO2 and water, you form either CO and water or C and water. C as a solid, pure carbon, that's soot. And that soot is the black that is formed on the bottom of this crucible. The problem is carbon is a solid, that soot is a solid. So when I record my third value, my mass value, and my fourth value, actually what that includes is some of the soot. So my mass is never going to decrease as much as it should because some of the loss of the water is now being mitigated by the fact that some carbon has been added on. So for that reason, the value that you record for how much water is lost is always going to be a bit lower than what it actually was, and hence your value for X will also be lower. The third part of this question asks you to list 2 assumptions made in this experiment. As we discussed, we identified the fact that assumptions are that the compound isn't decomposing or oxidizing, that we have lost all of the water of crystallization, and that all of the mass that has been lost is only because of water being lost and not because of anything else. So in this question, they actually never asked you to calculate the value of X. It's purely theoretical. But if you did need to do that, you would do so in the same way that we just did for the easy paper 2.